Hello, everybody. Thank you for coming. Incredible. So many are interested about the future. Well, I can tell you I'm not predicting the future. I just want to show you something about the future. So, my name is Felix Petriconi. I'm probably one of the C++, I wouldn't say dinosaurs, but I think I'm working with C++ since '94. And since more 14 years, I'm development manager and programmer at Mewis Medical Solutions in Bremen. And we build medical applications. I'm especially working on a product for displaying mammograms for breast cancer detection. And beside this, I have some C++ hobbies or things which I engage a little bit. So I'm a blog editor on the ICP website. We have a great user group in Bremen. I'm contributor to the ST Lab Concurrency library, and I'm a member of the ACCU conference committee. I have a great family at home who supports me in what I'm doing, and for the remaining time, I spend on classic film scores. Okay. Every talk starts with a quote. So the C++ language is too large for anyone to master. I think I want to disagree with Kate from this morning. She said that one has really to understand the language. I say the language is so complicated that nobody really knows everything. And it was not me who said this, but it was Sean Parent in C++ Now. So forgive me if I make mistakes. Please give me a hint that I can correct these things, but I definitely don't know anything and don't know everything. I mean, so why I'm here? We have an application which is heavily working in a parallel way, and we used over time many different ways to distribute the work on different CPU cores. And it's pretty easy to make there lots of mistakes. And maintaining the code is not that nice. And then in 2015, I listened to the CPP cast with Sean Parent about concurrency, and it was very impressive, and I wanted to learn more, want to be better, wanted to be better in this area. So I asked if I may contribute to the library, and said, well, yes. And from that on, I really had lots of fun there. It's sometimes very hard because he's very, well, he has lots of experience, and therefore he points me to some pitfalls or mistakes that I make, but I'm happy that I can learn this a lot. And I care a lot about sharing this knowledge, and that's what I try to do here. So, question is, why are you here? So, who has used stud futures? Okay. Who has used boost futures? Okay, a little bit less. Has anybody already looked into ST Lab futures? Wow, great. So, still everybody thinks that he's in the correct talk? Then we start. So, why do I have to talk about concurrency? Who knows from the origin of this quote? Yeah. Pardon? Yes, that's Herb Sutter. And it's from a paper we wrote in 2005, and we said that we have to change the way as we program. Why do we have to do this? We have this problem. We have here on the axis the number of transistors, performance, and the number of logical cores. And that's the way what I'm concerned at the moment. So for many, many years, it was pretty easy. We just could gain more performance by just having a newer CPU, and everything runs faster. But this changed about at this time point when he made this quote. Because we couldn't gain any more, or the CPU speed could not could not be increased anymore. So there was only one choice by the CPU manufacturers. They could more cores on the CPU. So, and typical desktop CPU now between 4 or 16 cores, that's quite normal. And for servers, they already have much more cores. So then we have a problem. We want to use them, otherwise our performance will not go up. Yeah, but there's there's a problem at this point. Amdahl's law? Who's familiar with Amdahl's law? Okay, it's surprisingly that this a different group of people than they say they're using futures. So what that is said, that there's a certain speed up depending on the number of cores. So fine so far. But it depends on synchronization of the work that has to be done. So if you make this as a graph, so this is ideal situation. So if you have 2 cores, then you get twice as much performance. If you have absolutely no synchronization between the things which are running on the core. So, but does anybody has this situation at home? Yes? You have?
Yeah.
How?
So, I was running simulations, and each simulation was running different parameter set. It was completely independent.
Yes, and has each of your CPU cores has a different memory bank? So, so even in this case, you have limiting resources, and there's synchronization happening that you don't see. So then we come to the point, for instance, if we have just 10% synchronization, that's not much from my point of view. At the beginning, it's not that bad. But if you, for instance, go for 16 core, you would expect that you have, or try to reach about 16 times the performance. But you just get something about, well, 6.5 of the performance. And you have more synchronization, the things got much, much worse. So if you have 90% synchronization, you shouldn't probably use multiple cores. You should stay on one core. Then you are faster. That's what this graph is saying. Okay? So, how could we use these multiple cores? Well, one point is that you don't use kind of multi-threading, you put your task in individual processes. Then, of course, you still have this kind of synchronization, what the colleague already mentioned, but it's a fair way, and as far as I know, for instance, at Facebook, as Andrei Alexandru told me once, they're going, in many cases, they go that way. They just have single-threaded way so that don't have some kind of synchronization issues at all. Probably not all their code, but certain areas of their code. So that's a valid way to go. The other thing is that you have one process with multiple. Without synchronization, it's more or less the same picture. But normally, there is some kind of synchronization between the things that you have to do or that you want to perform. So then we come to the point that we have synchronization, so that we need synchronization mechanisms. So this is just a collection of possible things, which I would call low-level synchronization primitives. And one purpose of this talk is I would not go into those, because there's other talk that you should use them. It's online by Sean Parent. I can recommend it very much. So what I want to talk today about is high-level abstractions. So about futures, channels. Another one is actors. That's something I will not talk about. I just wanted to name it. That's another technique to use. Okay. What's a future? I think so, since so many know this already, I perhaps can make this a bit faster. So future is a mechanism, so you have a function on one side, and you separate the function from the result. So at a certain point, when the function is done, the result will later appear in the future. Okay? So it's some kind of magic as it appears there, because it's not visible for the user that it appears there. This is there was added with C++11, but it's not a new technique. It's pretty old, from my point of view. And it was invented or discovered this kind of technique in the end of the 70s. So there are certain building blocks that you can have with futures. So one thing is, or that you probably want to use when you use futures. So one thing is that you have a task, and when the result is there, then you want to do something else with the result. So and you can chain them together. So that's what it's called continuation. The other one is join. So you have two independent tasks that they run or independently. At a certain point, you want to join them because you need both results and then continue from there the computation. Another way around is you have a split. So there you compute certain things, and then you say, well, now two different people or two different functions really need this result, and the computation of this should run independently. So then you split the result into two directions. And the third one, which we think one should support, is cancellation. What I mean with this. For instance, you have this kind of graph. It's a chain of tasks, and so you start here, and then in normal way, this will just compute through, and then you get your results in F3 and F4B. But it may be that the user just canceled, for instance, certain operation because it took him too long, or he changed his mind. This often happens. So then this result is not needed anymore. Okay. Then we don't have to calculate it. So this calculation, there's no need to execute it. And then these futures are not needed. And it should remain a graph like this, says collapse to its minimum, so that we really can save one of the most expensive resources which we have in the machine, CPU. Because that's the whole goal, that we want to distribute our tasks on as many cores as we have in the machine. So this is one property which I think a future should have. Okay, let's have a dive into the C++11 standard. So, all the further stuff I will explain with source code. And if certain things are not clear, please ask. I will try to guide you through it. So this is a very, very simple example. So somehow you want to know the answer on the question of the universe and everything. And you have a way how to calculate this. So it's a function. So what you do, you start with async. You try to initiate an asynchronous operation, provide this function object, and what you get is a future on the result. So you might do something. I don't know. Have somebody read the book? Hitchhiker's Guide to the Galaxy? Ah, okay. So, as you know, this might take longer. So, but at a certain point, you won't probably get access to value, and in the standard, you do it with get. Fine. So, and then, well, this would be then the output of the small program. So, other times, things can go very bad. So an exception might be thrown. Okay, we do the same. And in this case, we have to encapsulate our access to the future value with try catch. And be prepared that this exception might appear. And in this case, it will at the moment, and you try to get it, because the future contains the exception as well. And you end there. Okay? So far, so clear? Okay. What's the problem with this code? If this is your goal, you want best CPU utilization. Yes?
Blocking.
Yes. Blocking is bad. It's very bad. You probably have other things what you could do. So this is, I think, a big problem in the standard futures. Okay? And on top of this, there's no way to check if the future is ready. If there would be an option to check if it's already, so that you could try is ready or something like that, that would be better. But at the moment, it doesn't exist like this. So you are stuck.
There's one of this.
Pardon?
I think you can wait for no time and see if it's ready. Like this. There's a wait. It's not an official way. There's no thought is ready. But
okay. Okay. But it's not nice. So let's have a look at the capabilities of the futures which we have from 11 to 17 with no continuation. We have no join, one of the properties what we wanted to have. We have no split. We have no cancellation. There are ways to model it, but it's not nice. There's no kind of reduction. So if you have a future, it does not collapse to a future. So if you have more complicated graphs, this could be an issue. Or the code could be very ugly. There's no way of process monitoring, so there's no built-in way so that you can give the user feedback, well, you're already at 30%, 40% or something like that. It's not there. And very important as well, there's no way to say where this task shall be executed. Yeah, you just get which comes from the standard and its implementation. As far as implementation, it's up to the implementer that they spawn a thread or they do it on the thread pool, but you don't have real control where it is running. So the other thing is that it blocks on destruction. So even if you try to cancel you want to destroy the future because you're not interested anymore in the value, you cannot do it because it blocks until the task is ready. And these are the problems which we already talked about. And as well, it does not behave as a regular type. Okay. As a side note, the slides I make later on the slides available, so of course you can make pictures of them, but slides are easier, especially if there are some kind of links in it. So let's look into the boost futures. So they support continuations, and they're realized via .then. Let's have a look. So as well, we have our task that we want to calculate, and then we want to do something else. So we want to report, for instance, the result. So we create our first future, and then we call .then with the second task, and we got a second future which then will be ready when both tasks are done. Okay? Okay, same here. So as well, they support when all and when any. That's the way as they call it, join. So when all, who was not in Rainer Grimm's talk yesterday where we already introduced some of these things? Okay, so when all means that it will continue when all the futures which were passed are ready, and then will then take the result of all futures and proceed with it. And when any means that when any of the futures which we passed to when any is ready, then it continues with this result. Okay? So we have our two futures. So we know this calculation of the answer takes probably very long, so we split it because there's a way to split it. So we create two futures of this, and with when any we combine them and put them into a continuation. Okay? And at the end we have the result. What is the type of F? Pardon? Sorry, could you be?
It's I said tuple of futures, but it's probably futures.
No, it's even worse. Sorry, it's a future tuple of futures. Okay, so that is the signature of F. Sorry, that's a type of F. Who likes writing such code? Pardon? Yes, auto helps here, but it does not help here. And, pardon? Yes, it could help, but nice, I think. Okay, I will. Okay, so most of the things which are available in Boost are specified in the C++11 TS. So we have their continuations, when all, when any, but a real split is not available, and many of the other things which I think are necessary are not available as well. There's a way to provide a custom executor, but all the other things remain. It's the same problem. And there's the other thing, the std future and the std experimental are in different namespaces. As well a problem. Okay, but there's a new future. It's available at that location in the STLab repository on GitHub. And look what we have. So we have continuations. When all, when any, split, cancellation, reduction. We don't have progress monitoring so far, but we have it already in our agenda to implement it. Custom executor, it does not block on destruction, behaves as regular type. It has just one dependency, and that is boost optional. Okay? Some people might argue we have it in 17. That's true, but currently our library just requires C++ 14. Good. Let's have a look. Of course, we have different includes. Just at this very first slide as an example, we have, again, our problem or the task that we want to execute. Well, I just moved up a slide a little bit. So at this point, everything lives in the STLab namespace. And as a first parameter, we always give async the executor. So there's a place where the task shall be executed. Currently, we have 3 executors available in the library, but you can very easily implement your own. And For Windows, Mac OS, for Abstractions and for Pinnacle, we have built-in default executor, so that's the best way how to schedule your task if you're interested that they execute, for instance, on the step rule. And of course, then you have to pass as last argument the function that you want to copulate. And this altogether then returns, or this is then the future. Okay? So, this is just for illustration and purpose. I want to emphasize this. Polling on a result is not a good idea. So it's just want to illustrate that we have in the library a real get try, so that returns false if the future is not ready. But we have other ways, or you should always try to avoid this. Okay? This is just for illustration, not for using in that way, please. Okay? And then at the end, you access it, and with dot value, you get your result. Okay, as well, we have something explicit so that you really know what's happening here. It's a blocking get. So your application stops at this point until the result is there. Not a feature what we recommend, but it's just for completeness. It's in the library. Okay, as well, we support, of course, exceptions. It's pretty the same. So at that point, it's the same as in the standard as in Boost. If you wait here for instance, with a blocking get, and there was an exception stored in the future, it will be rethrown on if the result is there at this point, and you can proceed what you want or handle that exception. Okay. Of course, we have continuations. So again, we have we want to know the answer. Later, we want to report the answer. And then we create first our first future, and we create our continuation, and then we just pass the answer. And now here's the difference to what we had before with the standard. Here, in the standard implementation, the continuation, so the continuation is called with future. So you get, as in the continuation case, you get the future as parameter. In the SDLab, you get the real value. Okay? So, and then we have the same. Great. Yes?
What happens if the user is really fast and types something before the future of the transfer page? So it doesn't block the instruction, but what are the semantics? What do you need?
You mean this in this sample application?
What happens if the user writes something to standard in before the future finishes?
So if done goes slow.
Yeah, well, the future will destruct it, and you would do a cancellation on the future.
So it's not UP, it's well defined.
Yes. Yeah. Okay. Another thing which looks a little bit scary. I tried to split it up so that it gets a little bit clearer what's happening here. So I tried from in out. So in the inside, you have a function that returns a future. Okay. So this then returns a future of int. And this is then passed into a continuation. And this continuation is attached as a different feature. So at this point, we would get here, we get a feature of int as argument into the other one. But that's something what we wanted to avoid. So we wanted to avoid a future of futures. So that's what happening here is the reduction of futures. I don't know if it's clear or it's not clear. Yes? It's clear? Okay. That's great. Good. Yes?
Why is there a practical reason to do async inside them?
At this point, it's an example. It might be that some other thing or some other function just returns a future. It's just in this small example I used async. There might be other reasons that that created the future. Okay.
One of the possible reasons is, for example, if you're communicating with a server and you want to continue the first reply with another request to the server, which is again an asynchronous operation, and you want to join multiple asynchronous operations in ping-pong. And that's why the .then that supports return straight.
Okay. The answer was a little bit long for repeating. Okay. So if there are further questions, please come back, come after the talk, and we can go then for the details. Okay, now we do a join. So again, we split our very long operation on 2 tasks. And we want to join because we are not interested in the individual results, but we want to have the combined result. So again, we do a when all. We specify our executor, then the joint operation. And here's the difference. Again, we take the arguments as a value, not as future. Okay? And then we pass the futures at the end. Okay? Good. So, now we come to a split, which was not possible with standard futures. So, we have again our computation, which takes very long, but there are 2 people which are interested in the result. So, one shall go to Arthur Dent, the other one to Marvin, because he's very depressed. So we just have a continuation on the same future. That is what's not possible so far in the standard. Okay? I think it's obvious that one would like to have something like that, but it's not possible. Okay? So, and then we have our result. Good. There was one point. This at the end is not very nice. Of course not. But we have something else what we could use here of our building blocks. Well, has anybody an idea? When all. Correct. Okay. We just pass the 2 continuations in our when all, and then this will proceed when both continuations are done. And then we have a better way of going. Yes?
Why would you need a different executor for when all?
The question was, why do you need a different executor for when all? The point is, if you don't use it, or if you don't specify one, which one do you want to use? The executor of the first future, the executor of the second future, they might be the same, they might be different. Okay? Good. I don't want to go very deep into the executors because I have other things what I want to talk about. So executors are in general used to express where the task shall be executed. There are different kinds which are one can think of: thread pools or serial queues, main queues, which we need if you want to update your UI in your application, because many UI frameworks normally don't like it if you try to update it from within a thread. Or there's certain operation systems or libraries support that you can specify certain groups, so that certain operations should really just be executed on this one because there is reserved or special hardware for this, and other things then are executed on other groups. So in Boost, the executors, as far as I remember, have to derive from a common base class. That's not what we do in STLab. In the STLab, you just have to implement the call operator. That's all what you have to do. So at this point, implementing an executor, it's, I think, pretty easy. And at the very end, which I will not go in detail here, but it's at the end of the slide deck, there's an implementation of an executor for the Qt main loop. So just an example, and this is really illustrational. Don't ever do this in this way. This will not work. All the other applications really work, and all the test code really works, but this will not work. It's just for illustration. So the idea is that you have a line edit that you want to update when a certain operation is done. So we have our function that returns our answer, and this will run on our default thread pool, for instance. But the continuation we want to run in the Qt main loop, because only there it is allowed to update the GUI elements. So at this point, you just pass a different executor in the continuation, and there you are safe to update your elements. Good. These are just roughly some of the things what we want to do in the near future for the library. So, small conclusion for the futures. I think that Fuchsia is a great concept to structure your code in a good, readable manner, so you don't have to deal with ugly code, how you put it on threads, spawning threads, canceling threads, and all this stuff. And if you do it in a correct way, you can do it even with minimal contention. But the futures have a disadvantage. You just can use it once. So you build up your complex graph, you trigger it once, and then the complete graph is gone. You have to reset up it again. And channels are one concept that supports these multiple invocations. Okay, small introductions. As well as futures, it's possible to create a graph of executions. And this graph is persistent as long as it's in memory or you destroy it manually. So it's as well a pretty old concept. It's described in a great book by Tony Hoare, and I can really recommend it. And the nice thing is the book is now open sourced, so you can download it and read it. So just another illustration, because in the following slides I talk a lot about sender and receiver. So you might see this as a pipe. So on one point of the pipe, the sending side, you push in the values, and on the receiver side, there's a process that really calculates the values. And then you can build graphs, so we can do as well a split or a join and all these things. So that's an example for what I call a stateless process. So at the beginning, we have our sender and as a receiver, and we tie them together and create a channel. And then we have a process that should then do the work. So what we actually want to do at the end of the channel. In this case, it's just a simple example. It just should print the values. So attaching the process to the receiver is pretty easy. We just do it with the pipe operator. So you know it from the notation in the Unix command shell. You pipe the operation one after the other. Same idea here. Then you have to set that the receiver is ready, and then you can start sending the values into the channel. And at the end, of course, all the values drop out at the end, the processed values. If you want to do a split, it's the same as with the continuations. You have on the same receiver, you do twice, perform twice in concatenation. And here's an example of this. Now I changed a little bit the notation. Now we have structured binding in C++ 17. So this, at the beginning, this becomes much nicer. And so we have two processes that should print independently. One printer A, which we attach to the receiver, and printer B, which we attach to the same printer. And then again, we send our values into the channel and get the result. This result does it look always like this, or can it look differently? Yeah. So that depends. Since the channel works on the default executor, so on a thread pool, so it's not defined in which order the results appear at the end. At the same time, we support join, so that it's the same as the when all in the futures. So you continue when you have all your values or a set of values. And so in this case, you have two values coming from upstream, and when both the values are ready, then you continue with this pair downstreams. Zip is like a zipper, so they go in a round-robin manner. It takes the value from the first upstream, and then from second, third, and so on, and vice versa. And the third one is it takes them as they come in. No predicted order. Just the functions which we have so far. Additionally, we have possibility to limit the work on the different processes. So if you, for instance, certain processes might have huge resource, or need, for instance, lots of memory, and you do not want to overflow the system. So you can limit the number of items that are waiting on a certain process. And as well, it's possible within the concatenations, and so when you have within the pipe symbols, you can put there in between the executor, so you can change the executors in the graph. So for instance, for the very last thing, you can put an executor which just runs in the main loop, or so that you can update, for instance, your UI elements. Okay, then let's see. Some problems have state, of course. Or if you have an end-to-end relationship between your input and output values. So for instance, in simple example, you have one value goes in, and you want to double it so that in the output it goes twice the same value. For this, it's not possible with a stateless executor, so with a simple lambda, for instance. And for this, we have stateful processes. And as well, sometimes it's a problem. You have a process that is ready to receive values, but there's nothing is coming from upstream. Perhaps you want to react on this. And this is, of course, not possible with this stateless process because there is no, if it's not called, it cannot do anything. So, in this case, when you want to implement a stateful process, we did not have a base class that you have to implement, but your stateful process has to implement this signature. So it needs an await function. So this is the point where all the values come in. You have just a single upstream, then this is just one value. If you have multiple upstreams, so if you have a join, for instance, then there are two or three or more upstream values, and then at this point the await has to take as many arguments as you have upstream sender. And if you await at a certain point, of course, you have to yield. So the process should generate some kind of output. And we need a way to tell the system in which state the current process is. So I will later give an example. And optional, there are ways to close the process or to handle error situations. But I don't want to go them at the moment. So this is just a small example to illustrate how this stateful process works. The idea of the application is you start it and it adds so many numbers that you enter at the keyboard until you enter a 0. This should be the trigger. So now I want to get the return of the sum of all values. So I will come later to this adder. First, the main. So we create our channel, and we have our receiver, and to the receiver we pipe our stateful process, and at the end, okay. So this is our adder. So of course, when we want to sum up certain weights, this is our state, the sum of the values which we want to calculate. The initial state is that we await forever. So we wait as long as values coming. Okay, so we get the values, we add them to our sum, that's what we want to do. But in the case we got 0, then we say now we are ready to yield. So we are ready that this value, the sum of all values, should go downstream to our printer. Okay, so we change the state because after calling await, the framework will call the method state and will check now is the process ready to yield to value so that we might proceed. Okay, and then we are called yield. We have our return value. We set our process back into the initial state. And we return the sum of all values. Okay? So, this is very short introduction of channels. More is not possible in this time frame. But if you're interested in this, I'm happy to tell you more about the possibilities, about timeouts and all the features which we have here. And so this the channels close the gap where the futures are just allow one kind of execution. Okay? So, small takeaway. Really use high-level abstraction if you want to distribute your work on different cores. Don't do it with, I commented. Use whatever you have it, use a custom or a ready-built thread pool. Try to avoid to build your own one. It's very complicated, it's error-prone, and it's likely that you get it wrong or that it really waits as well. So normally the operating system implementers know this far better than we. Okay? Be in mind that try to design your application that it works deadlock-free, regardless if you have just one core or many cores. Because there are subtle things when certainly, even if it works often, it suddenly does not work, or it stops, or it blocks on deadlock. And the futures help in this way. Yeah, and most important, don't sprinkle your code with thread, mutex, and atomics. So they don't belong into your application code. They belong really under the hood because they are low-level primitives. Use the high abstraction. It's much better. It's much more readable, your code at the end. It's much cleaner, and it's easier to maintain. Okay? So, small acknowledgement. My family, who supports me a lot on this work. Sean Parent, who taught me many things in this area, gave me the privilege that I may use his presentation. My company, who gave me the opportunity to be here, and all the other contributors to the library. Okay, that's far at this moment. So, here you can reach me. I'm very welcome on feedback. Now, anonymous, I don't care. It's always, I try to improve my presentations all the time, and I'm very welcome on feedback. Are there questions? Yes, please.
In your example with channels. Thank you. Yeah. In your example with channels, I guess it's an example, but you feed the values one by one to process in the pipe.
Yes.
Would it be possible to pipe a range as inputs and as outputs either an output iterator to collect the result back or some kind of a join function to get one result out?
At the moment, not. But of course, you can, as a first thing, you can add a process, which a stateful process, which takes, for instance, an array of values, and then it works, picks one value after the other and sends them downstream. So at the moment, this is not a built-in feature, but you can build it very easily by your own. Okay? I don't see anything.
Hi. So one of the benefits of using tasks and .then continuations over previous implementations, which might have been things like delegates and callbacks, is that it's very readable from the point where you're actually looking at the code. You can tell what the flow is asynchronously.
Exactly.
We're doing this, then we're doing this, then we're doing this, and then we're finished. For channels, it would be really great to have that same kind of structure as well. Is there any work ongoing to, so instead of just piping the lambdas, to have it kind of inline like a .then, but with channels? Is that possible?
My current thinking is we might go the other way, which is with the pipe operator.
So my current thinking is we might go the other way, which is replace .then with the pipe operator. Just find it more readable, so you don't have to keep nesting the with parentheses. So just go pipe, pipe, pipe whether it's a future or a channel.
It's more about having the code in the same block, so it's code here, and then the next bit, and then the next bit.
Oh.
The sequential lambdas almost, instead of having the lambdas defined at the top, and then piping together the names of the lambda.
Oh, you can pipe directly to a lambda.
Yeah, you can.
So you can inline the lambda. Yeah. That's fine.
I just did it in a way that I prefer the way, so some kind of functional way, so that you have a certain thing, and probably it has already a name. So it's a certain thing that you want to process or want to calculate, and that you later attach this to the chain. Of course, you can take lambdas and pipe them one after the other. That's no problem.
Hello. I'm here. Thank you for a nice talk. I have a question. Maybe I missed this part, but what about continuation for errors? I mean, I've seen only example for continuation for result, and this is a big difference between like your version and the boost version, where you get the mutex into continuation, which you can check and you can get like exceptions thrown out of it.
This is something which we have, which I missed or which I skipped in this talk, which is called a recover function. Mm-hmm. So there's a way that you, in case of an error, that you can recover from this problem and then continue. That because of time, I skipped this, but I can hopefully can bring this up. Just give you a small overview. So that's the homepage of the ST Lab. And if you go for libraries and for concurrency, so there's a complete documentation. It's online. It's similar what we all know from CPP reference. And for all functions and all test examples are already visible on the very first page. So you just can go here and see somewhere we have a recover example, I think.
Third line.
So there you see how it's possible to do a recover.
Thank you.
Okay, sorry, it's very small.
Yeah, but it's fine.
I'm very sorry. Okay.
Is it possible? Sorry, is it possible to use recover together with with then?
Sorry.
Is it possible to use recover and then together?
Yes.
So, yeah. Thank you.
Is there any way to skip typing before the executor?
Yes. If you don't specify a new executor on the continuation or the recover function, the previous executor will be taken. That's true for the futures and for the channels. So you inherit or you get a copy of the executor from upstream, and as long as you don't specify a new one, it takes the same one as before.
Even for the first time?
No, for the first time you have to specify one. No, well, you can write your own one. So you can write your own one that does the same, but so that it encapsulates this under the hood. But as far as the library does not have this.
I want to add something to the question about the error handling. And my question is here.
Sorry.
And how do you handle errors when joining futures? So when using when any, for instance?
I didn't.
I mean, you showed us an example how to connect multiple futures, right? Through when all, and probably you have also when any, right?
Yes.
And when one futures, you connect.
So in the when all case is, as soon as one error occurred, all the other ones are cancelled, and then you continue. Continue. In the when any case, many errors might happen. If the last one succeeds, then this will trigger the continuation.
Okay, thank you.
Okay.
Thanks. Do you have deferred execution? And how does that apply to that graphs of execution?
What do you mean with deferred execution?
So in the boost future, there's an option to schedule a task for deferred execution, so it's executed when you call .get.
So I'll answer that. We don't have a .get, so we don't have a lazy execution model in there.
Awesome.
Hi.
Hi.
Great talk. Is there a way to cancel in-flight tasks in the case of joining with, no, in the case of when any, if a task encounters an error, is there a way to cancel the other tasks in the chain to signal them?
Yes. So if the task is already running, it's not. It's never killed. Not built in. But you may could do this by your own. So in when any is so. So when the first task succeeded, it tried to cancel all the other ones because there's no need to execute them as well. But if they're already started, they will run until the end and the result will drop on the floor. Okay? Okay. I think we are already over the time. So if you have further questions, please come here. I'm here until 7. Sorry, until 5. Then unfortunately I have to leave. But I'm open to all questions, and I'm open to miss the next session if you have questions. Thank you very much.